Okay, so one of the main reasons for starting this channel in the first place was to conduct experimentation to better understand Nikola Tesla's ideas pertaining to electricity. Now, the experimental aspect is one part, but we kind of have to keep up with the theory aspect of that and have the two sides sort of complement each other. And one of the first difficulties which someone may encounter when they first start reading this stuff and trying to understand how Tesla was thinking about electricity is that he had a completely different conception of electricity than we do nowadays. And this kind of all revolves around ideas pertaining to the ether and what the ether is and the sort of functions it performs. This is something that I'm still learning myself, but we'll try to kind of cover a little bit of the basics here just as a sort of primer into the subject. And maybe I'll give you some references that kind of helped me when I first got going. But yeah, it's an ongoing study. I'm sure I'll be trying to figure all this stuff out, for the rest of my life. But yeah, I figured it'd be good to just do a video on sort of the basics of a field-based theory of electricity as opposed to a particle-based one. Now, I was trained as an electrical engineer, so I did undergrad and master's, and I'm currently doing a PhD in electrical engineering. So I do have all of the standard, ideas in my head as far as what electricity is and how it affects phenomena. And when you go to school to learn about electricity, what you're taught is the electron theory. And you have these positive charges called protons and the negative charges called electrons. And these are actual particles which are extended in space and have some sort of size and mass and electrical charge. Now, the protons and the electrons are thought to be equal and opposite in charge. So there's this idea of some sort of qualitative difference between a positive charge and a negative charge. And what we get into with ideas pertaining to the ether is that there is really no such thing as a particle. And what I mean by that is that the differentiation between what we will classify as particle and not particle is not so much a difference in substance, but a difference in the motion of the substance that makes up that particle. And as opposed to talking about positive charge and negative charge as two different entities existing at once, we're going to be talking about something more like compression and rarefaction of a single substance. So we create a sort of overabundance and a sort of want of that substance. And those are the two conditions of the substance which we can call positive and negative, or charging and discharging. And we're going to try to get into all this stuff in this video series I want to do. So for now, let's just kind of go over the basics of what the ether is and kind of where the ideas pertaining to that originated and how they developed up to their culmination in the early 19th, late 1800s electrical sciences. So we're going to go over that right now. So when I first started kind of getting into all this stuff, Tesla was the first scientist whose books I read, and he didn't necessarily write a whole lot of books, but he does have the lectures published and has patents. But his lectures were kind of where I started, his 3 lectures. And those are the ones that I'm kind of going over and trying to replicate as closely as possible on this channel. And I kind of just started reading him sort of cold, not really knowing what I was getting into. And when he talked about his theories about electricity, I didn't really know how to make sense of what he was saying. Because in my head, I was conceiving of this as a phenomenon due to the action of electrons. And if I were to think about electricity flowing down a line, I would say, oh, it's the flow of electrons. And you would picture, all these little charged particles kind of bumping into each other down the line. And that's not at all what Tesla was talking about. So there is a pretty steep barrier to entry to this stuff. And one of the first things I did after reading the lectures and trying or having the want to understand more what he was talking about is I looked to his contemporaries, and come to find out, he's not the only one talking about this ether stuff. This is kind of what everybody was talking about back in the day, especially in the electrical sciences, but not just in the electrical sciences. It was all over the place. That was just sort of the thing back then. And I started looking at books from a lot of other famous electrical scientists, a lot of the Maxwell papers. Oliver Heaviside wrote a whole lot of books, or papers, which were turned into books. Charles Steinmetz, J.J. Thomson. These are all the guys who, they are credited for developing a lot of the mathematical concepts or theories behind our modern day electrical practice. But the ideas which they had about what electricity was and how all this stuff actually works is not at all, what we're taught today. So I kind of started reading into all this stuff and started developing a little bit better of an idea of what is meant by the word ether. So I guess where it kind of all started, now ideas about the ether have been around, since the ancients, for thousands of years. There's been all sorts of ideas as to what the ether is and how it behaves and what sort of functions it performs. So it's not necessarily like a new concept or some out there concept. Where the story kind of begins as far as our modern day physics is it was conceived of as the medium in which light propagates. So we know that, a sound wave is alternating compressions and refractions in a medium. And the medium in which that sound wave propagates is the air, which is made of fairly coarse molecules sort of floating around in the atmosphere. We maybe don't necessarily think about light as being similar to a sound wave propagating through its own medium, but that is the ideas that they had back in the day. You could kind of compare light to a sound wave or a series of alternating compressions and refractions in a medium, and that medium being the ether. Now, one of the necessities of this is, since the velocity of propagation of the energy in the medium is dependent on the properties of the medium, based on the differences, the huge difference between the speed of sound and the speed of light, it was thought that the ether had to be an incredibly dense medium. And there were multiple different theories that were sort of popularized as to how this medium actually worked to propagate energy through it. We worked through different longitudinal theories of light, and then after the plane polarization was discovered, it was thought that light was a transverse vibration in the medium. But basically that's how kind of all this ether stuff got started. It was just a medium that existed somehow in space that allowed these light, the very fast alternations to propagate light. So what it was basically is, if you had some sort of luminescent particle, it would be oscillating, expanding and compressing at incredibly high rates. And it was these that was causing the propagations through the etheric medium. And that's kind of why it was referred to as the luminiferous ether. It was the medium upon which light propagated. And that was kind of how it was conceived for some time. But the place where it kind of started to take more importance in the physical sciences or the electrical sciences was with Michael Faraday. So he was sort of like the master experimenter. He was very famous for kind of popularizing electric study. He was at the Royal Institution and would host these huge classes where all the townspeople would, come in, and he would kind of show them what he's been working on and what he's been experimenting with. But he had a very wide breadth of discoveries across different fields like electricity and chemistry. And he's pretty widely regarded as, one of the best electrical experimenters there was. But he conceived of the electric action as being mediated by these lines of force, which existed in space. And let me see if I have a marker around here. Basically, we know that if we have charged particles, so let's say this is a positive charge and this is a negative charge, we know that if we have charged particles, these particles interact with each other, and the way they were thought to interact with each other is by these lines of force that can be observed between the two particles. So if we had this sort of positive and negative combination here, what we would observe is some pattern that kind of looks like this between the two particles. And nowadays we say, well, that's lines of force. But then you kind of start to ask questions like, well, what do you actually mean by that? Lines of force of what? And if you assume that electricity is just mediated by particle interactions, pretty quickly this idea of a field surrounding a particle makes not a whole lot of sense. What he was conceiving was that the action on these two particles was being mediated by these lines of force. Now he calls them, they were called Faraday tubes back in the day, but what he was thinking about these, or the way he was thinking about these, was sort of as hydrodynamic vortices. So these are like little whirlpools of motion that existed inside of a medium and sort of originated and terminated on charged particles. And these whirlpools of motion interacted with each other, so they exerted a force on the neighboring Faraday tubes. And that's why we get this structure where they're sort of pushing away from each other, is they're exerting a force perpendicular to their axis here. And it was these things, and they exert a force perpendicular and a contractive force when you have the positive and the negative. So you can kind of think of these as attempting to pull the two particles together as they interact with each other. And you have the Faraday tubes from a single charged particle terminating not just on some neighboring charged particle next to it, but all the other particles in its neighborhood. So you can kind of picture Faraday's conception of what was going on as you have this charged particle which exists at some point in space, and it has these sort of tubes which connect it to all the neighboring particles around it and are sort of pulling it in every which direction. And when you get the electrical force, when you have that electrical force evidence itself and the charge is pushed or pulled one way or another, that's due to these tubes pulling it due to an excess of pulling force in one direction as opposed to the other. This idea was not necessarily popularized right away until a guy by the name of James Clerk Maxwell. He was kind of inspired by Faraday's idea that the action which we see exerted on these charged particles doesn't just happen instantaneously across space with no sort of mediating phenomenon, but he thought that there must be some sort of medium which propagates this action, or which can account for the fact that one particle can interact with another. And he kind of took this idea and developed it mathematically, and he came up with the quaternion expressions to demonstrate how the displacement current from charged particles can affect the medium around it. That's actually what Maxwell is kind of famous for, is this idea of a displacement current occurring in the dielectric. And he had a little bit of a different interpretation of it than Faraday did, but he came up with a model for the ether where it was sort of composed of these sort of whirlpools of motion, and in between these neighboring whirlpools of motion there were these little electric particles, and as the whirlpools were sped up or slowed down due to dielectric displacement, so a charging or a expanding of the whirlpool of motion, it would exert an outward force or an inward force, which would sort of push these charged particles around. And it's those displacements in the medium that was responsible for the currents flowing through the medium. Guys like Oliver Heaviside took this and kind of ran with it, and he wrote quite a lot on the subject, and it takes a long time to get into. I got to go back and read all that stuff myself, because I read Heaviside kind of right when I was getting into all this, and I'm sure I could get a lot more appreciation out of it now. But he thought of the electric action as being conveyed by a medium. So electricity is not just charged particles flowing down a wire, but it's really this sort of churning motion, this compressing, expanding, and rotational motion which occurs around the conductor. So the conductor isn't necessarily where the action is occurring, not inside the conductor, but it's really more of some sort of guiding structure for the action to occur around. And actually he talks about the frictional resistance on the conductor as being a source of loss. So basically the conductor is eating up all the electric induction in the medium surrounding the circuit geometry, but it's not actually the main channel for this electricity to flow through. It's really more of like a discharge terminal for the electrification to dissipate itself into via resistance. And this is something that you can kind of get a better feel of when you start reading the Heaviside books, as well as the Steinmetz books. So the first thing I kind of read by Oliver Heaviside was this electromagnetic theory book. There's a lot of math in it, but if you can kind of breeze over the math a little bit and read his explanations of what he's trying to get at with his equations and how he's conceiving of this phenomena, and you can kind of get some sort of idea as to how he's perceiving this electric action taking place inside of the medium. And this book here, if you've done any research into the theoric electrical sciences on YouTube, you've probably come across this book before. But that's Elementary Lectures on Electric Discharges, Waves, and Impulses by Charles Steinmetz. And it really is kind of a landmark book, because it is able to sort of mathematically demonstrate the idea that the energy in an electrical circuit or system is not just inside the components in the system, but actually exists around the system. Basically, when you turn on some sort of generator or input supply to a circuit, you're actually storing energy in the area surrounding that circuit. And the way, or the situation in which this energy stored in the circuit, the situation where this really comes out is in these transient phenomena, which Charles Steinmetz is trying to mathematically describe and explain. And he has some really good analogies where he relates like electrical transients to mechanical transients that we're kind of more familiar with. And we get a sort of a better idea of what's actually meant by, the energy in an electrical circuit actually exists around the conductors, but not necessarily inside the conductors. So that's kind of what we're working towards, is an idea of some sort of medium which this circuit geometry exists inside of, and we're acting upon that medium, creating these rotary motions. And there's all kinds of speculations as to how this medium is actually disturbed and how the electrical action actually affects it. But that's kind of the gist of it, is we have this medium and we're creating either compressions, rarefactions, high potential, low potential, or high pressure, low pressure with our impressed EMF. And then the medium will sort of exert motions to try and level out those stresses or those differences in potential. And that's kind of the cause of the electric current. So the way that I'm kind of thinking about it now is we have this dielectric action where we create some sort of displacement in the current, or create that disequilibrium. And that displacement or that disequilibrium is the cause of the motion or the electric current. And we can go into this for a very, very long time, but that's kind of the basic overview, roadmap. That's where we're going here. I think that's kind of what I want to start doing alongside the experimentation that I'm doing on this channel. And I'm getting ready to do another one soon here. I actually ordered a vacuum variable capacitor, some old Russian thing, to put into this circuit here. And that's going to allow me to get much finer capacitive adjustments on my resonant circuit. And I think once we install that, we'll get some really good output on this thing, because the capacitor increments that I'm allowed on this capacitor bank, it's too coarse for the tight bandwidth that I have on this transformer. So I really do need some finer adjustments. But hopefully this week that'll be fixed. But anyway, I was going to say, alongside the experimentation, I want to start doing videos on the actual theory behind this stuff. So I think what I'm going to do is kind of start by going over the work of Tesla's contemporaries, or people who kind of influence the ideas of electricity as pertains to the ether. People like Heaviside, Charles Steinmetz, and J.J. Thomson. And then we're going to try to get just a more, all-around understanding of, what is actually going on here on this tabletop. So, yeah, this is the first video, but I think that's something I'm going to probably try to start doing from now on. And it'll help me learn too. I do have to kind of, go back over this. It's been a little bit of time since I've read all these things the first time through. So it'd be good for me just to, make these videos and review all these ideas again.